Welcome, welcome. This is an exciting day. We're going to do a lot of firsts. But what I want to do to start with is I want to be consistent and point out. Remember this at the beginning of the semester? I said these are some things that we're going to do. And when we do them, I'm going to write the date on it, to be honest, so that you know that I was telling you the truth about where we were headed. So I just want to point out we've hit 2 of these already. So we've learned how MRI scans work, and we've learned how carbon-metal bonds can lead to new carbon-carbon bonds. That's the theme we're going to continue today, but we've already seen those too, so I just wanted to be honest there. Okay, so what I'm going to do next is a bit of a review. Nothing on this is new. This is exactly what we saw before. And, hold on. What happened there? There we go. And all I wanted to remind you was this issue of the carbon-metal bond. So here we have a Grignard reagent, and that Grignard reagent has this carbon. Give me a second to get this tuned up. There we go. It has this carbon-metal bond, which means the carbon is nucleophilic. And that's what makes Grignard reagents so interesting. Now, oh, wait a minute. I think somebody's calling in. Is that the magnificent Victor Grignard?
Yes, this is the magnificent Victor Grignard here.
Can you tell my class about your magnificent self and your magnificent reagent?
Certainly. I am magnificent. See my magnificent mustache? But as for my reagent, it is magnificent because it has magnesium. When you react a haloalkane in ether with magnesium metal, the magnesium inserts between the carbon and halogen atoms to make the magnificent magnesium reagent named after me, the magnificent Victor Grignard.
Well, what makes your reagent so magnificent, Victor?
Well, because of the carbon-magnesium bond, the carbon is nucleophilic and reacts with electrophiles such as epoxides to make new carbon-carbon bonds. Yay! That is magnificent! And the best part is that my Grignard reagents are not that basic, so they can even react with aldehydes, ketones, and esters. You're going to see that a little later.
That is magnificent.
Peace out from here.
Okay. Now what we're going to do is I want to summarize a number of things. This is on the handout for this week. We talked about alkyl lithium reagents, we talked about Grignard reagents, and we mentioned Gilman reagents, but we haven't really talked about them yet. What I want to do is I want to compare and contrast, because they're all similar in that they have a carbon-metal bond so that the carbon has the negative charge, the carbon acts as a nucleophile. But these reagents are not all the same. So one of the things we've been talking about in office hours and in the review session is this concept of a base versus a nucleophile. So a personality of a molecule can be defined as being electron-rich if there's an electronegative atom that has a lone pair of electrons, or in the case of these reagents, a carbon with a high area of electron density because it's more electronegative than the metal. That can be a nucleophile, but it can also be a base. It's context dependent. Those are not something that you say that is only a nucleophile, that is only a base. You can't say that. It can be a nucleophile when there's an electrophile around. It can be a base when there are protons around. So the question is, are these two properties, nucleophile and basicity, the same? They're related. Personalities are similar, but they're not exactly the same. You can be a good nucleophile and not a strong base. You can be a strong base and not a good nucleophile. We have to tell you that. It has to do with some really complicated quantum mechanical things. So that's what I'm about to do. So alkyl lithium reagents They are extremely basic. So basic, in fact, it limits their use. Starting Thursday, we're pretty much only going to use alkyl lithiums as bases. They are really strong bases. They can be used as nucleophiles, but it's pretty rare. Grignard reagents, on the other hand, are a strong enough base that they will deprotonate anything in terms of a functional group that is either more or as acidic as an alcohol. Does anybody know-ish what the pKa of an alcohol is? 16, I love it. It's exactly right. The pKa of about 16. Anything that acidic or more will be deprotonated by a Grignard reagent. So I'm setting up how strong of a base it is. Gilman reagents are different. They are the least basic of the group. So these are the only reagents that are capable of reacting with, and this is where things are going to get pretty cool. So I'm just going to list these, and we're going to describe one of these reactions in detail. I'm going to give you an example, but this is a primary haloalkane, or this is called a vinyl halide. So we've got the halogen on an sp2 carbon. Warning, you don't know how to make those. And also, if we make, and this is something that's going to be a major theme of the class later. So I'm going to leave these alone for the first part of the semester. But if we have a 6-membered ring with 3 bonds in it, that is a special situation. We're going to call it aromaticity. You'll hear all about it. Don't care to really go into details now, but I want this in your notes, that this is called an aryl halide because for historical reasons, molecules that had a 6-membered ring with 3 alternating double bonds, that is an incredibly stable situation, and it's referred to as aromaticity. Has nothing to do with smell. That's just historical, why that connection was made. Therefore, we call it aryl halide. That's not that big of a deal, but this reactivity is. Now, I want to point out that if you're using the electronic version of the handout right now, I usually get a lot of questions about Gilman reagents. So if the technology is working for me, that is a hot link to a video I prepared that explains more, so right here, that explains more details than I really care that you know, but a lot of students have questions about it, so it's like about a 5-minute video. You can watch that. Nevertheless, let's talk about Gilman reagents. And what I'm going to do is I'm going to draw one. If you remember from last lecture, it's got a copper atom, and it's got a lithium, and it's got 2 alkyl groups. And again, the video explains details of this. We're not going to use Gilman's very much, so I don't want to take 10 minutes of your time. I'd rather you just watch the video because it's not really going to be that important. But what we're going to do is we are going to react this with a vinyl halide. Now, what I'm about to do is not nomenclature. This is not nomenclature. I found that when we start making reactions like this, it's helpful for me to number the atoms. So I'm not numbering these as if I was naming them. I'm numbering them simply so you can keep track of what I'm doing. So what I'm going to do is I'm going to put a number 1 here, a 2, a 3, a 4, a 5, and a 6. Again, this is not nomenclature. I'm just putting those there to keep track. And to keep track of these, I'm going to do the same thing. I'm just putting a 1, 2, 3, 4. So what I just said up here is that Gilman reagents, as opposed to the others that can't do this, only Gilmans can react with these species in a reaction that we're not going to go through the mechanism of. This is one of the few times this semester I'm just not going to do the mechanism. All I'm going to tell you is this is not an SN2 mechanism. Even though it's tempted to think it is, it's not. It has to do with the copper atom and things we're not going to talk about. So it's not SN2. I'm not going to tell you what it is. You're not responsible for it, but something really cool happens. The alkyl group on the Gilman reacts and displaces the bromine to make a new carbon-carbon bond. That's why I wanted to keep track of the atoms. So let me number these to be consistent. And what we've got right here is a new carbon-carbon bond. That was weak. That's okay. We'll do another one today, so I'm not going to try it again. Okay. A new carbon-carbon bond. That's pretty cool. The Grignards, the alkyl lithiums cannot do this. Only Gilmans can do this. Now, there's something else here. We need to balance this out. And so you get copper salts. It's not all that straightforward. I explained it a little more in the video, but you are not responsible for writing these structures. It involves some chemistry that we're just not going to talk about. Watch the video. It's called Gilman Reagents Explained. And hit it on the top of the website, top level. It's helpful, short videos. Click on that, then hit Gilman Reagents Explained. There's some other videos on there as well, but if you want to see it, that'll explain the copper salts. It's just not part of the class. Okay, it's there. All right. Uh-oh. Uh-oh. I think we've got somebody who's kind of angry. Wait a minute. I think he's really angry. Is this Henry Gilman calling? The Iowa State chemistry professor?
Yes, this is Henry Gilman.
I understand you're a little upset about me calling Victor Grignard magnificent.
Of course. What's up with that? If Grignard is so magnificent, how come his magnesium reagents cannot make new carbon-carbon bonds with primary haloalkanes, vinyl halides, and aryl halides like my copper reagents.
Okay, so I see your point, but we wanted everyone to remember magnesium, which sounds a lot like magnificent when you think of Grignard.
Seriously? That is pretty cheesy. Just like Grignard's mustache, by the way. I know, because my reagents have copper. What if you call me incomparable? The incomparable Henry Gilman.
Okay, you're officially the incomparable Henry Gilman.
Peace out from here.
They have a thin skin, don't they? They're just so easily they get upset. Okay. I do want you to remember that. So what you're going to find is a month from now, I hope you remember magnificent Victor Grignard, magnificent magnesium. That's the goal, is to set that in your mind, because that can be a little bit harder to remember than you think. Gilman reagent copper, incomparable Henry Gilman, magnificent Victor Grignard. That's the idea. Okay. I'm going to switch gears a little bit because how did you find the first homework? The synthesis problem was tough? Okay, I'll tell you this. We are not going to grade that synthesis problem. We're not going to grade any of the synthesis problems, period. I wanted you to work through it, so I didn't want to say that ahead of time. But I wanted you to work through it, but now we're going to talk about synthesis. Because in so many ways, this is an important part of the class. I'm not just going to assume it's from last semester. In this semester, it is all about the new carbon-carbon bonds. And what synthesis really is the ability to generate more complex molecules from simpler ones. It's a three-step process. I want you to be extremely systematic. And this is one of the many times I'm going to have to say, please trust me on this. There is a systematic way of doing this that may not be necessary at the beginning of this semester. It will be necessary at the end. So that if you use discipline now and you adhere to this methodology, by the time we get to very complex cases, you're going to be fine. If you take some shortcuts and do it different ways, you're going to get to a point where you get buried and you would not have had practice in doing it right. So with that in mind, there is a three-step process that is going to be very helpful this semester. Step number one, chemists, in particular one chemist from Harvard, came up with this really classy way of saying something. And you probably have heard this before, but it's referred to as retrosynthetic analysis. I'm going to carry out a retrosynthetic analysis. That sounds pretty good, doesn't it? So like if you talk to your parents and they say, what did you talk about in OChem? What are you going to say? Exactly. Doesn't that sound good? They're going to go, whoa, care package on the way. What is it? Work backwards. That doesn't sound great. Don't start at the starting material and try to get to the product. Start at the product and do the last reaction first. Work backwards. You got to trust me on that. That's the way to do it. In the meantime, something else you do is you count carbons. Bless you. Count carbons in the starting materials and products. Now, in this class, we're always going to require that all the carbons in the products come from the carbons in the starting material. I'm just warning you, that's always going to be the rule. So every carbon in the product had to come from the carbons that we list in the starting materials. That's always going to be a constraint. There's a reason for that I'll go into as the semester goes along. It makes sense. But anyway, why would we do this? Why is this important this semester? Right. We're making new carbon-carbon bonds. He's exactly right. It lets you figure out exactly where the new carbon-carbon bonds are. And that's going to be critical to what we're doing. And then a third thing, which is new this semester compared to last semester, and it's something that I've leaned on more and more heavily. We used to stop there. We used to work backwards, count carbons. And then we completely changed. And now I want you to learn to recognize the key recognition elements. That's what these are. That's what these are for. We call these KREs, key recognition elements, in the product. This is why you work backwards. In particular, this tells you what the final reaction in the synthesis has to be. Because you identify the new carbon-carbon bond, you look for the other key recognition elements, you say, aha, that's a reaction that I know, so now I know exactly what the last step was. And then you draw the starting materials and reagents for that, and then you go all the way back, and you keep going backwards until you get to the starting material, the very beginning starting materials. So that's the strategy. Work backwards, count carbons, look for the KREs. So let's go through an example. I'm going to give you a reaction that we've learned, and we're going to go through the KRE just to remind you what I'm talking about with the KRE, just to be really clear on it. What I like to do is I use two different colors when we're going to combine things, because it's easier to see that way. So what we're going to do is we're going to react this epoxide with this Grignard reagent. And what I want to do is I'm going to number my carbons again. This is not nomenclature. This is just keeping track. Makes it easier to keep track. Remember, this process is a two-step process. In a second step, the chemist opens the flask and adds H3O plus or H2O HCl, same thing, mild acid. That adds a proton to quench it. Go ahead and write the product of this reaction. This is the one we did on Tuesday. And I'll write it as well. Whoa. It's not what I wanted. Okay, any questions about that? Yeah.
You said HCl was a mild acid. I thought it was a strong acid.
So you use very small amounts of it. So this is a solution of usually about 1 normal HCl, which if you put your finger in there, it wouldn't even sting very much. Don't do it. I got to be careful when I say that. This is not like sulfuric acid where we're talking super strong acid, put your finger in there, it dissolves. This is just a very weak acid solution. but you're 100% right. HCl is a strong acid. So I'm glad that is so important, by the way. I love it when people ask questions. It never feels to me like it's a challenge. I really need to know when the words I'm using aren't making sense. And I totally understand why you would say that. It's like, I said weak acid and I write HCl. What do I mean? I should have been more precise. A dilute amount of HCl, we're not doing any damage to the molecule with strong acid. That's what I'm getting across. I find this to be a really hard thing to do in lecture. Because on the laboratory bench, I reach for my one normal HCl. I know I'm not going to destroy my molecule, but it's HCl. So on paper, it looks the same as I take concentrated HCl, I destroy my molecule. And so I've got to try to find ways to kind of make that difference. But this is a mild acid wash. It's just adding a proton. Okay, the big point I want to make. This is your KRE. We have a new carbon-carbon bond that is 2 carbons away from the OH group. Do you see that? There's an OH group, and the new carbon-carbon bond is 2 carbons away from that OH group. That's the key recognition element of this reaction, which is the only one you know so far. It's your first reaction. That's the key recognition element, and it's always in context of that new carbon-carbon bond. So, okay, let's do this. Let's do a synthesis problem. And that's setting the stage for the synthesis problem. Okay, I'll move it later. Whoa! That's not what we wanted. Then synthesis example. Here we go. I'm going to give you this as a starting material. You're going to do some magic, and you're going to end up with this product. All the carbons of the product have to come from the starting material. Now, I think you'll agree that this is somewhat challenging, and it's hard to figure out immediately by staring at it what's going to happen, but let's be systematic. So we're going to work backwards. We're going to work on that last reaction first. But what I want you to do is count carbons. So if we count carbons, how many carbons are there in the starting material? Okay, that wasn't very enthusiastic, but I'll go with it because it was the right answer. How many carbons are in the product? 8 carbons. So clearly, what did we do? We put 2 of the starting materials together to make one product. I've got to figure out how to turn that off on here. I'll do that. Okay. Now, what does that tell you immediately? It tells you that that is the new carbon-carbon bond. Why? Because that's the only way you are connecting 2 4-carbon fragments. So you immediately, by counting carbons, have identified the location of the new carbon-carbon bond. That's the point of doing it. More than that, what we want you to do is that third step and say, okay, what I've got now is I've got that new carbon-carbon bond, and how many carbons away is it from an OH group? 2. So now, without having to spend too much time worrying about it, what reaction has to be taking place to create that product? The Grignard plus a what? Well, no, an epoxide. So remember, it's a 2-step reaction. The Grignard reacts with the epoxide. We wait for that to happen. Then we add the acid. So we know immediately, and now we also know which side had the epoxide and which side had the Grignard reagent. Is the black side the epoxide or the Grignard reagent? It's the epoxide. So just by looking at all of that, you can figure that out pretty systematically. So what we've got is we're going to have our second step, which is mild acid. But we know that what we started with was this epoxide. And because we're being nice and it's during lecture, this is not chiral. So I don't have to worry about any chirality here. So that's the epoxide. What is the Grignard? And let me move that a little bit. I think it'll make more sense if I just move it right there. What does the Grignard look like? The red side. Are people with me? So now all we have to do is figure out how we are going to get to that epoxide from the starting material. Does that look possible? What reagent are we going to use? MCPBA. That's one version of, it's a per acid. That's what the PBA means, per acid. But we can write MCPBA. We'll give you full credit for that. I'm going to write it as RCO3H because there's a variety of per acids. That 3 is not a typo. That's real. That's it. I don't know if you knew what MCPBA was, but it's a R with a chlorine, a benzene ring, and then C, 3 oxygens and a hydrogen. So that's MCPBA is fine. That's a per acid. There we've got our epoxide. We're looking good. What do we make our Grignard from? We talked about how to make a Grignard. How do you make a Grignard? You react what with a chunk of magnesium metal in what solvent? Magnesium metal and ether, those two are always required. That ether is important. What's the starting material for that? Exactly, a haloalkane. It's going to be that haloalkane. How do we get that haloalkane from the starting alkene? We need to add HBr, but is it Markovnikov or non-Markovnikov? Non-Markovnikov. Did you guys learn non or anti? Anti, yeah. So it turns out, this is a little quick timeout nomenclature. I always say non-Markovnikov. It's the same thing as anti-Markovnikov. My problem with anti-Markovnikov is the very first reaction you generally learn with that. The hydroboration reaction adds syn, not anti, which confuses everybody. So I just say, look, let's just call it non-Markovnikov. Anti-Markovnikov is fine. We'll accept that. It's the common usage, but it drives me nuts because a lot of the reactions that are non-Markovnikov are actually syn, not anti, which drives everybody nuts because that's not what the anti is referring to, and I probably did more harm than good by explaining that. We got it right. It is ZAP, HBr, HNu, or heat. There we go. Synthesis 100% correct. And it was very systematic. Any questions about synthesis? Yeah? You actually need to split that bond, so you need light or heat. You can use either. That's HNu, that's light. You can put heat there as well. You have to pop those apart to get the initiation for the free radical process to occur. Okay. This is so cool. I'm going to set the stage for like 4 lectures. This is so cool. And once you understand this, you go, oh, this is really boring because you're saying the same thing over and over again. And that's the point. I am going to say the same thing over and over again. But I don't want to be boring. But I might be. Functional groups such as carbonyl groups undergo characteristic reactions. They have a personality. And before you know anything about carbonyl groups, you can figure out what that is. So let's talk about it. In particular, there are common themes, and all the different reactions are variations on the themes. And notice I'm not specifying, those aren't meant to be methyl groups. I'm not telling you what's on the carbonyl. There's going to be 3 chapters worth of different things on those carbonyls. But the general C double bond O, that's kind of the center anchor chemistry of second semester. And let's take a look at what that looks like. Bye, Henry. Bye, Victor. Here we go. And I'm going to take an example that has 2 hydrogens, but it has that double bond. There's the carbon-oxygen double bond. Now, the thing to always remember is that on that carbon-oxygen double bond, there is a pi bond. There it is. There's your pi bond. But the big story is this. What I'm doing is I'm plotting the electron density on the surface, and then I'm looking where there is high areas of electron density, where it's going to be red, and where there are lower areas of electron density, it's going to be blue. Green is in the middle. And I want to have this sit in your mind as the visual. So when you look at the C double bond O on your paper, I want you to be seeing that. The big story here is that pi bond, and the big story is the fact that there's a lot more electron density on oxygen to make it red up there than there is on carbon, which is why it's blue. Those are the 2 things I want you to have in your mind. So let's go back. As you see that, let's go back to here and say, all right, there is, let me put a color on that. There is excess electron density on the oxygen, and there is a partial positive charge on that carbon. Great. So let's now define several chapters worth of reactivity. If I am a nucleophile, where am I going to react on a carbonyl? Who says oxygen? Who says carbon? Exactly. We got to work on their enthusiasm. We got a lot of these. Nucleophiles react here. If I'm a proton, where am I going to react? Carbon or oxygen? Much better. Protons, we'll talk about this later. Lewis acids also react here. Okay? Now here's the sneaky part. That pi bond. That pi bond acts as a pseudo leaving group and breaks when a nucleophile reacts at the C atom. So this is the game changer. A nucleophile can react at the carbon, and instead of something having to leave, it just breaks the pi bond. Pretty simple thing to do. That's what's new about second semester organic chemistry. If, on the other hand, you add a proton, it's going to go on the oxygen. So we have defined the personality of this carbonyl species, and that's something to keep in mind at all times. So whenever you see a carbonyl, I want you to think of that. I want you to think of that color. And never forget that underneath there is a pi bond that can break if we attack that carbon. Okay. Now, early on, I came to the question. No, okay. Yes, good. Early on, I came to the conclusion that I could go through the next 4 lectures and give you 6 or 7, no, probably 10 or 11 different reactions with mechanisms and not point out something that was obvious. But so now I decided to point it out at the beginning. Those 6 or 7 or 8 or 9 or 10 or 11 reactions, they all have the same mechanism. The reagents are different, but they're the same mechanism. And in fact, we're going to go to different chapters, and we're going to have related mechanisms. So for this entire unit, which is going to go on a lot longer than you want it to, we're going to see reaction after reaction, make all kinds of cool new reactions happen, make some new bonds. It's going to be cool. But we're only going to see 4 different mechanisms. So they all come in 1 of 4 categories. So made up the names, A, B, C, and D, very creative. And this is what we're going to talk about. There are 4 common mechanisms seen when carbonyl compounds react with nucleophiles, with and without acid. In this class, to make the point that these are common mechanisms with different reagents, different players, we make that point. We call these mechanisms A through D. And they come in standard formats, and we're not going to describe them in detail today, but I gave them to you for reference. And it's variations on what you can do with protons on oxygen, nucleophile on carbon, and a pi bond that breaks. Variations on that theme depending on what is here and what is there, and what's the nature of the reagents. It'll all make sense systematically. There are the 4 mechanisms, A, B, C, and D. They're not nearly as complicated as you might think. Instead of describing them in detail, we're just going to go look at a classic example of mechanism A. So let me first say all those mechanisms are just there for your reference. All of these mechanisms have a tetrahedral intermediate. What do I mean by that? What's the hybridization state of the carbon, of a carbonyl? Sp2. When the nucleophile attacks, we break the pi bond. In each case, the timing of a proton is different. But as we attack that carbon, we turn it from an sp2 to what? sp3. Sometimes it stays there. Sometimes it goes back to sp2. But in each case, we have that tetrahedral intermediate. So we go from sp2 to sp3. I want to point that out because that's always going to be an intermediate you watch for when it comes to these mechanisms. So whether it's here, there, or there's always a tetrahedral intermediate. The timing of the proton is what's different. What we're going to focus on right now is a simple one. Mechanism A. Mechanism A I can define in a really straightforward way. Mechanism A, use this with strong nucleophiles. And what does it really come down to? First step, make a bond with a strong nucleophile. Where is that nucleophile going to attack? What atom of a carbonyl? Carbon. Add a proton. Easy peasy. That's mechanism A. Make a bond, add a proton. Okay. We're going to talk about our first reaction. But before we do, I want to get you really in tune with some interesting chemistry. So we're going to take a bit of a break. So here's something we're going to do as often as I can. I am about to talk to you about something that will absolutely not be on any exam, but I think it's really interesting chemistry that's very relevant to what we've been talking about. We're going to call these molecules of the day. Not going to be on any exam. But I think it's really cool. The first one, we're going to start off strong, really strong. We're going to talk about how pharmaceuticals work. Really, how do they work? So we've all taken pharmaceuticals. We go to the doctor, you've got a problem, the doctor prescribes something, you take it, you get better. Not very many people on this planet understand what's going on after you swallow that pill. Why does it work? So let's talk about a problem right now. Who has cedar fever? Oh, it's been raining. If this was like not raining, everyone's hand would go up. Okay, you've got allergies. Who knows what allergies really are? They're not cool. So let's face it. As a species, we did not evolve to perfect our social interactions by making it so that we have this gross stuff coming out of our nose, and if we're not careful, we're going to spew it all over everybody by a supersonic sneeze. That obviously makes very little sense. What in the heck is going on? So let me explain this. 40,000 years ago, we slept in places that were not particularly clean as a species. In particular, anything that was open while we were sleeping is a place that worms would crawl in. Not kidding. The worms would go in because they could live inside of us and do really bad things. So we had to evolve a mechanism to keep the worms out. In particular, our noses were vulnerable. Our throats were vulnerable. Worms could go in, start eating us from the inside out. That's bad, right? So here's the strategy. A worm goes in your nose. It triggers a response. That's because your nose recognizes the molecules of the surface of the worm, and it releases something called histamine. It's like, uh-oh, alert, there is a worm in the nose. The detection cell releases histamine, and that histamine goes to another type of cell that has, and here's the correct term for this, if you want to talk about it in mixed company, a highly viscous proteinaceous solution. We call it snot. So there are cells that hold a lot of this highly viscous proteinaceous solution waiting for the histamine. The histamine comes along because a worm was detected. The cell releases the snot. The worm is like, I am slipping and sliding. And just to make darn sure there are no more worms in my nose, I am going to cause this entire being, this human being, to use all of the air in its lungs, expel it as fast as it possibly can at supersonic levels through your nose. That worm goes flying and hits the cave wall. That's what we evolved to do, is to keep the worms out. The problem is that, unfortunately for us, the molecules on the surface of pollens look like worms. So even though there's no threat to us, this is the response that we get. We can't stop it. The pollen is absorbed in your nose. The molecule is detected. Worm alert, worm alert. Histamine is released. The snot is released. You sneeze. And you are having to apologize to everybody around you because it doesn't really work out so well. That's the story. So we've all experienced this. And what do we take, especially if you're a little kid, what do we give a little kid that has allergies? Starts with a B. Benadryl, exactly. So let's take a look at why Benadryl is useful to keep the sneeze from happening. Wake up, Mr. Computer. There we go. Molecules of the day. Benadryl. Okay. That is Benadryl on the left, that's histamine on the right. Let me tell you what's going on. Benadryl goes in and it... That's Benadryl on the left, that's histamine on the right. Benadryl is what kind of molecule? What's it called? It's called an antihistamine. Why? It's because the way the histamine works is there is a protein that is shaped like a lock if you think of histamine as the key. The histamine goes in. It actually causes a change in the structure of that protein because it fits perfectly. It activates, snot's released. The whole process starts. An antihistamine, and this is the way most drugs work, looks like the histamine, but is not. It goes in, it binds very tightly into that lock, but it doesn't turn it. It goes in and does not activate. That's called an antagonist. And that's what pharmaceutical scientists will talk to you about. Benadryl is an antagonist of the histamine receptor. So it goes in, and then the histamine bounces off, so you cannot activate it. So you coat your receptors that would have released the highly viscous proteinaceous solution. They are now blocked with the Benadryl. Now, here's the problem. The Benadryl does not look like histamine. That structure is not anywhere near the same. So the question is, why is Benadryl a histamine? Big finish. Here we go. Hint, it's related to the most important question in chemistry. Exactly. So let's go over here, and let me make that a little bit bigger. That is histamine. This is Benadryl. I think you'll agree these don't look very much alike. However, I heard it already. If we ask the question, what's the most important question in chemistry? We'll get a clue as to what's going on here. So I'm going to now activate my calculations, and this is Benadryl. Excuse me, this is histamine. See those two areas of high electron density and where they are in three-dimensional space? The reason Benadryl is an antihistamine is because when we do the same thing, ready for the big reveal? Check it out. Yeah, that's why pharmaceuticals work. Is because in three-dimensional space, those areas of high electron density are exactly in the same orientation. So it fits into that lock, but then the other parts don't allow it to activate. So it goes in, blocks it, it's an antagonist. That's how many, many pharmaceuticals work. And so we're going to go through a whole lot of different examples of this, but this is just one example. And I'm going to set up the next one, which is, in many ways, the next one we're going to do is kind of one of my favorites. There's a problem with Benadryl. If you're a parent, it's not really a problem in most situations. What happens when you take Benadryl? You get sleepy. I mean, that's why most parents will say to a child walking onto an airplane, oh my gosh, you've got the sniffles, here's some Benadryl. Oh, you think I'm kidding. You'll do it too. And so it turns out that histamine is used for various things. In our nose, it's used to release the snot. I don't know what to say. That's what it's used for. In our brain, it controls wakefulness. So unfortunately, at the same time we're controlling what's happening in our nose, the Benadryl is going into our brain and it's making us sleepy because the histamine was part of the system that controls our wakefulness. So it's a side effect and it's something we have to deal with. And we're going to follow that story. And again, none of this is on an exam. We're going to follow that story in a lecture or two. All right. We're ready. Let's go. Grignard reagent reacting with a carbonyl. I'm going to give it away. There is no mystery here. I'm going to give it away. This is mechanism A. Because Grignard reagent is a strong nucleophile, mechanism A is what two steps? So what are we going to do? Let's make a bond. This is a nucleophile. Where is it going to attack? It's going to attack the carbon. What happens to the pi bond? It breaks. So we make a bond. Go ahead and draw the product of that step, remembering that the magnesium bromide is going to attach to the oxygen that has the negative charge. Remember that. Lewis acid, Lewis base complex that forms there. So go ahead and draw this product. Now notice that little asterisk. We created a chiral center. We started with a non-chiral molecule. We created a chiral center. That means we created a racemic mixture. If I was even meaner than I am, I would have you draw both of those with wedges and dashes. That literally gets totally out of control really fast. So what you're going to get used to is we want to keep track of the fact that the intermediates are chiral and maybe racemic. Put an asterisk on the chiral center, write racemic under it, and then we're all good, and you can use just lines. But we know that that's actually two compounds, one R, one S, that were created because the nucleophile can attack the carbonyl from either side with equal probability. So we get both enantiomers of that intermediate. It makes it impossible to keep track of on these mechanisms if we have to draw all of the chirality all the time. So you're good. Put an asterisk to designate it to chiral center. Write racemic under it. You'll get used to this format. Okay. Now, the thing to remember is this right here is your, whoops, come on, there we go. That is your Lewis acid, Lewis base complex. I keep emphasizing that because it's easy to forget it, but it's a pretty tight bond there. It's not just a salt thing. So we need to keep track of it. Okay. The next thing that happens is a chemist opens the flask and adds mild acid, a very dilute solution of HCl in mostly water. Simply going to add the proton. Draw the arrows and show what happens. So draw that final product. Now, you will get used to this. It seems arbitrary, but you'll get used to this. When it comes to the final products, we want to see the stereoisomers drawn as wedges and dashes. We just don't do that for the intermediates, but we do it on the final product. So the final product is actually 2, and it's 2 different enantiomers. However, as you'll notice, we're in the sympathy category really fast by doing that, but that's okay. We made another new carbon-carbon bond. This is so cool. And now we've got a different KRE. So let's take a look at what this KRE is. We have a new carbon-carbon bond, and we have an alcohol group. How would you describe that new carbon-carbon, that new KRE? We have a new carbon-carbon bond on the same carbon as the alcohol, which is different than 2 carbons away that we saw last time. So another way to say that is it's got an OH group attached to the same, I'll just write it out, instead of saying carbon, C atom, as the new carbon-carbon bond. Pretty cool. That's the KRE. All right. Let's use this. So I was very ambiguous about that starting carbonyl. It can be an aldehyde. That means it has a hydrogen on the carbon of the carbonyl. Or it could be a ketone, which means it has carbons attached on both sides of that carbon, of the carbonyl. So let's look at all the possibilities of what we get out. So let's carry out this reaction on so-called formaldehyde, which is a gas. If we have formaldehyde, we use an ethyl Grignard in the first step. That's what the 1 is for. We mix those together. Then we add a proton. Remember, make a bond, add the proton. Second step, these numbers tell you they're not happening at the same time. Because, by the way, if you mix the Grignard with that mild acid, it would just protonate the Grignard, done. Huge, expensive mistake. So you've got to wait till the reaction happens with the carbonyl. When that's done, then you add the mild acid. Okay? Go ahead and write the product there. So just follow it through. And I'm always going to keep the carbonyl containing piece black here. and the Grignard is going to be red. But we make a new carbon-carbon bond. And notice that's a primary alcohol. We added one carbon to that Grignard, and we made a primary alcohol. Let's do the same thing, and this is a reaction we just did as the mechanism. So you already know the product. So this is exactly what the mechanism sheet did, so that's why I did it so fast. But once again, we've got a new CC bond. Here. But because we created a chiral center, and because that reaction can occur on either face of that starting aldehyde, we get two products, but in this case, it's secondary alcohol. Let's just go one step further. And now we have methyl groups on both sides of the carbonyl. And we're going to carry out a Grignard reaction with that ketone. Who knows what this molecule is? Many of you have used it. That starting ketone. It's acetone, nail polish remover. We add an ethyl Grignard to that. Write that product. There we are. Let me move this around. Notice, because of those two methyl groups, we created a tetrahedral carbon, but it's not chiral. So we don't have to write wedges or dashes. You can if you want. That's not wrong. But there's no chirality. You certainly cannot write racemic because there's only one product, one stereoisomer, because it's not chiral. Okay, and this is the big finish, is this last one. Believe it or not, we can react a Grignard reagent with CO2. And what I'm going to do is I'm going to blow this up, make this bigger. And I'm going to draw the intermediate that one gets when you attack What did I do? I simply reacted the ethyl Grignard with CO2. Because believe it or not, CO2 is a carbonyl compound. Now notice what we end up with is this intermediate. Does that make sense? It's just following right along. Who thinks this intermediate is going to react again with another Grignard reagent? Because we have a carbonyl there, another one. Who thinks it's not going to react again and it's going to stay here? Okay, you're right. So even though there's a carbonyl in this intermediate, this is the tetrahedral intermediate, even though there's a carbonyl there, why doesn't it react with another Grignard reagent? The negative charge. So this whole species has that negative charge, and those two carbon-oxygen bonds are actually equivalent. You're exactly right. It's the resonance. It's the delocalization. So it is not a carbonyl anymore. Does that make sense? It's got a whole negative charge on it. You can't have a nucleophile attacking something with a negative charge. That's two negatives butting heads. That's not going to happen. So I need to write the charge. There's the negative charge I'm talking about. So this is not going to react due to the negative charge. Okay, we have 5 minutes. What I want you to do, therefore, is draw me the product of this, write it down before I reveal it, and talk to the people around you to compare to see if you get this answer right. So now, given that I just told you that that's the intermediate, and it does not react again with a second Grignard, go ahead and draw the product of this reaction. This is the big finish for today. So once you've written it, talk to the people around you, confer, see if you get the right answer. Yeah, question. Okay. Who feels confident? I got this right. I love it. Survey says it's carboxylic acid. So you can use a Grignard reagent reacting with an aldehyde or ketone or CO2, and you can create a primary alcohol, a secondary alcohol, a tertiary alcohol, or a carboxylic acid. That is a versatile reaction. This is one of the most useful reactions you will see in synthesis. So we started off really strong because this is a reaction you will see a lot of. There's lots of ways to make those aldehydes and ketones. And so you can feed into this in a lot of great synthetic strategies. Question?
Is there any reason that like the bromine magnesium in the oxygen, because that has a positive charge too, right?
So the magnesium, don't forget, has an overall +2 charge on it. And so that is going to make a much tighter bond to bromine than, it's not going to release that bromine. It comes as a unit. So the parentheses are around the magnesium and the bromine for a reason. That whole thing is a positive charge. Got it. Now, before we go, I have 2 minutes left. Before we go, spoiler alert. We're going to start class tomorrow, or Thursday. It's going to be super boring. Because what we're going to do is we're going to say, I know, let's use that nucleophile. It's a strong nucleophile. Oops, mechanism A. I know, let's use that nucleophile, strong nucleophile, mechanism A. So we're going to do the same thing. Mechanism A is what? With a strong nucleophile, and then, so we're going to do that twice in a row, and then there's going to be a plot twist. See you on Thursday. Yeah.
We did the mechanisms. Is it okay if I do line drawings instead?
Yeah, of course.
Okay.
Yeah, that's totally fine. You know, again, I do what I do to try to be clear in presenting, but I'm not saying what's the minimum required to get a good grade. If we know you know the chemistry, we're going to give you the benefit of the doubt. So any format that you draw, you can write all the hydrogens for all I care. But that's always going to be
Like
good.
on your exams, you're going to be writing them with the, not the line drawings, right, on the mechanism. So can I just like redraw them with the lines?
Yes,
Okay.
you can do that.
I need to go to work.
Oh, bye-bye. So, could you explain to me kind of, so you talk about not reacting again due to the negative charge on this oxygen, but what about this other oxygen?
They're equivalent by resonance.
Okay, so then we wouldn't have to draw another resonance structure with the single bond on that one? Oh, okay. Makes sense.
Yeah.
So I was wondering, Will you always indicate like the starting material? I know in a past class they gave us like 3 or 4 starting materials and it said make this ending materials. Will you always indicate the starting?
Well, okay, so always, I don't like answering that question because sometimes I'll give you products and say, what are the starting materials?
Okay.
But for synthesis,
Yeah.
the last
yeah.
questions on the exams, yes.
Okay.
Here are the starting materials that contain carbon,
Okay.
and here's your products. And you have to go from there to there in multiple steps.